Alright guys, welcome back. This is going to be the last electrophilic aromatic substitution video where we'll be covering the basic reactions. After this, we can move on to the more advanced sort of stuff with electrophilic aromatics. Alright, so what are these last two reactions left? Right, these are all going to be centered around adding alkyl groups to benzene. Right, so we added nitro groups, those sulfonation, we added the sulfur groups, we added bromine, chlorine. Now we're going to talk about adding alkyl groups. So the first reaction that we have is called Friedel-Crafts Alkylation. Alright, that's our first reaction. So I'll show you the basic scheme and we can go from there. Start with benzene. We need some sort of alkyl group, and we put a halogen on it. And we need a catalyst again. So we have a chlorine on our alkyl group, and we just put AlCl3. Right? Now I'm going to just color the carbon that the chlorine is on, so it's going to help you guys visualize how this adds. All right, because it's a little bit odd. I mean, it could be a little bit hard to visualize. Here's the product. It's going to look like this. So you see it attached to that secondary carbon right there. All right, if you want me to number it, 1, 2, 3, 4, and that's going to be 1, 2, 3, 4. So how does this reaction work? Well, what's going to happen is our chlorine, our alkyl group with our halogen, our alkyl halide, is going to react with that catalyst. I'm going to orient it this way. So the chlorine attacks our aluminum, and we're going to get this intermediate. Chlorine has a positive charge, and that aluminum gets a negative charge on it. Now what happens is we're going to form a carbocation, and this is important. You need to form the carbocation. This bond breaks and goes to the chlorine, giving us this intermediate. Alright, so that's what happens. We get this intermediate. Now what happens is our benzene, and I'm going to start over here, is going to attack our intermediate. Right, it's going to attack that carbocation, giving us this compound. So it's going to use a double bond, and remember there's a hydrogen here. So here's a hydrogen. Just put this way. Alright. And so it's going to have a carbocation here now. Those double bonds stayed there. And so remember we had this uranium ion, this sigma complex, and I'm not going to show it resonating around. You guys know I could go like this, and I could bring that down. So we're going to skip straight to the deprotonation. So what's going to happen is that chlorine from AlCl3, or AlCl4 at this point, but I'm separating that chlorine kind of. Negative charge on the chlorine, remember, on the aluminum. This bond from the chlorine grabs the hydrogen. Then this comes down. What this shows, remember, is since I'm using that bond, is that the chlorine detaches and uses that lone pair to grab that hydrogen. And now we finished, and here's our product. Alright, we added this alkyl group. Now, one thing to watch out, alright, that where there's a carbocation, there's a rearrangement possible, right? And so, what happens if I had this as my alkyl group? Alright, Chlorine attacks that aluminum, giving us this. I'm going to abbreviate a little bit. Now, I showed in the previous step, we just detach that chlorine and give a carbocation, but primary carbocations, they're not that stable, right? Remember we learned this in Orgo 1. They're not that stable. So what happens is, because we don't even want to form that primary carbocation, we're going to have a hydride shift. Now, the hydride shift is what kicks out the chlorine. It's a concerted mechanism, which means it happens at the same time. So rather than doing this, that comes out. I'm not going to worry about the chlorine and the AlCl3 right now. You get this as your intermediate, and then we get this hydride shift over there to give us this, right? What we're going to do is we're going to avoid that carbocation in the first place, that primary carbocation. The hydride shift is what kicks the chlorine out. So this hydrogen attacks that carbon, shifts to that carbon, and it kicks the chlorine out. So in one shot, we're going to get the carbocation here and that hydrogen moved over there. And then the reaction is going to happen. So you see that in this case, we're not just going to add that primary alkyl group like this. Remember, 1, 2, 3, 4. We're not just going to add that way. That's not going to happen. What's going to happen is it's going to rearrange to add like this. So you got to watch out for rearrangements. Okay? Remember, if your carbocation can be more stable, it will be. It will want to shift. All right? So always watch out for something like this. The next reaction we're going to go on to is called Friedel-Crafts Isolation. And I'm going to erase this stuff over here. Similar, but a little bit different, obviously, otherwise it would be the same thing. So I'm going to just change this. Acylation. So what's the general scheme? Benzene. And what we do is we have this acyl chloride. Now, acyl chlorides are very reactive. It's this carbonyl with a chlorine. It makes that it makes this carbonyl extremely reactive, right? So we have this acyl chloride, and we put this, again, a catalyst, AlCl3. And the product is going to be, and that R group is just some sort of alkyl group, carbon chain. And the product is just going to be this. Wipe away the chlorine and attach the benzene in its place, and you get this. All right? That's FriedelCrafts Isolation. Mechanism time. So we're going to react with the catalyst. Chlorine attacks that aluminum. Draw that better. Get this intermediate. Negative on the aluminum. Now what's going to happen is this bond with that chlorine is going to break. All right? And we're going to get this intermediate. Or actually, let's draw it vertically. Okay, carbon with a positive charge. And then Cl to AlCl3, negative on the aluminum. Now, we don't like this negative charge on that carbon, right? So remember, this is back to Orgo 1. This is a very special sort of intermediate. When we have this carbon with that positive charge connected to the double bonded oxygen, what happens is one of the lone pairs from oxygen, oh, my bad, comes down and forms a triple bond, giving us that intermediate, right? And that's going to put a positive on the oxygen, all right? And so this is an important intermediate, right? It's called the acylium ion, all right? So you should definitely know that this is the electrophile that's being reacted with. The acylium ion, not this intermediate here. It's the acylium ion that's the important reactant here. All right. So once we have that acylium ion, get the benzene going. It's going to react with him. So it's going to attack the carbon. Pick one of these bonds up. And now our intermediate is going to be this. Carbon, double bonded oxygen, and the R group. And here's our positive charge. Again, remember we can resonate this around in the sigma complex or the uranium ion, whatever you want to call it. We're not going to do that. We're going to skip ahead. Remember that there's a hydrogen here. And then we're going to deprotonate using this double bond from that, instead of the single bond from that chlorine to that aluminum. Grabs that H. This bond comes down, giving us this product. Let me make that a little bit easier to see. All right, and so we added this ketone essentially. We have this ketone off the benzene, and if you want me to rotate it a little bit, it would look like this. All right, so we added this carbonyl group, right? And so it's a very useful reaction. Now, one thing you guys should learn, so I said we had 2.5 reactions left. So remember how when we did sulfonation, it was reversible. Now this guy isn't reversible, but he also has another reaction we can do off of that product. So let's start doing, for what we have so far. All right, so if we add some acyl chloride with an R group, it could be any carbon chain, AlCl3. All right, we're going to get this. Right? That's our reaction that we just covered. Now, the little new reaction is called a Clemmensen reduction. All right, it's a reduction. This is how it's spelled. Oh, not bad. So we're going to reduce this guy over here. All right, and so it must be an aromatic ketone. So this reduction only works pretty much in this case, right? When you have that ketone coming right off of the right off that benzene, right? So what we write is we write zinc. All right, so we're going to put a zinc here, parentheses mercury over hydrochloric acid. And what that does is you just kind of wipe away your ketone. So essentially draw it without the double bonded, without that carbonyl, actually. Wipe away the double bond oxygen. And that's it. Now, you might be wondering, well, why would we do that, right? It's just puts this alkyl group, essentially, right? When I could have just done a FriedelCrafts Alkylation. Why go through all the trouble? But remember, alkylations are prone to rearranging. So if you wanted to add, say, this straight chain to be like this on a benzene, you can't do that with FriedelCrafts Alkylation. But if I just did this with the FriedelCrafts Isolation. Now let's see how many carbons. 1, 2, 3, 4. All right, 1, 2, 3, 4. If I just added this, we'd get this on our benzene, because there are no carbocation intermediates. So you'd get this, and then we just do Clemmensen reduction, ZN, HG, HCl, wipe away the carbonyl, and you get your alkyl group without any rearrangements, exactly how you wanted it here. If we tried to do the alkylation way with this guy, remember we end up getting a carbocation rearrangement, and it's going to look like this. And so our product using the alkylation would actually given us something like this. Alright, that is not that. So the Clemmensen reduction is pretty useful. It can sidestep a lot of the limitations of your FriedelCrafts alkylation. And so that's going to be it for the basics of FriedelCrafts alkylation, or of these electrophilic aromatic stuff. We're going to get into some more complicated stuff in the next video. Hope this video helped you guys. See you in the next one.